because it's a power system. And in the phase array or the other system, we request the high efficiency also. And of course, sometimes we need a high power. Business system, current business system, we don't need any high power, for example, to drive the IoT device or etc. But at last, my dream is a solar power satellite. As I mentioned in the first day, the other application, for example, to fly the drone or the other application, we need a high power, and user require much power to charge your mobile phone, etc. So in that case, high power is required, and hopefully, phase controllable technology is important for phase array to control the beam direction. And this is the most important for the radiative WPT. And this is a business side. Of course, cost is important. If we can develop a very excellent high power, high efficiency amplifier, but cost is, for example, $1 billion or etc., anyone doesn't use it. So in this viewpoint of the cost, it's very important. And additionally, this is a requirement for the microwave itself. We usually use a continuous wave only and a no modulation wave, because in the first day I explained you, based on the Poynting vector theory or the maximalization theory, we don't need any modulation as an energy. As an energy, we use radio wave itself. So we don't need any modulation, and continuous wave and no modulation wave are enough. Of course, we can modulate the radio wave to carry simultaneously power and information. It's a swift system. But to carry the energy is only, we don't need any modulation. And this is the viewpoint of the important viewpoint, lower noise. Because when we transmit, for example, even 1 watt, compared to the wireless communication system, this power is a little bit higher. So to avoid the interference to the existing wireless communication system, lower noise system is required. So based on this requirement viewpoint, we must design microwave amplifier with a generator as a transmitter. And this is a general figure to explain the relationship between the frequency and the average power with a lot of microwave generator and the transmitter generator and amplifier. Generally speaking, when we use the semiconductors, power and frequency are very low, usually. And if we need a very high power, over kilowatts, we have to use the microwave tubes. I'll explain the microwave tube later. But generally speaking, low power, we use a semiconductor, and if you need more power, we use a microwave tube. And based on the viewpoint of the cost, microwave tube is better. But in this talk, I'd like to introduce a semiconductor technology mainly. And this is a very, very general microwave amplifier design. At first, in the transmitter, we generate the microwave about 1 milliwatt or below. And after generating the microwave, we add some circuit like a phase shifter and microwave amplifier to use the radio wave as energy. So from the source, usually we use a 1 milliwatt microwave power, and with the semiconductor, we amplify this weak power to the convert it to the high power microwave. And here you can see it's a very general simple figures. Semiconductor here, and additionally now you see the matching two matching circuit only. and we can divide this semiconductor. At first, material and form we can classify. And usually, you mention sometimes silicon CMOS or gallium nitride FET or etc. But it's easy to divide the semiconductor device into material and form. Material is usually used as silicon. Of course, it's most most cheap device, and we can use all silicon devices, not only for microwave but also the IC or etc. And gallium arsenide is sometimes used for the hypermicrowave about 30 years ago or 20 years ago. And recently we are expecting silicon carbide or gallium nitride, and in future additionally gallium oxide or the diamond, etc. It's just a material itself. And with this material, we create the form of the HBT, MOS, HEM, FET, etc. as a semiconductor. So this is an explanation of the semiconductor devices. And additionally, with this semiconductor device, we must design the amplifier. And this is today's main topic, how to design the amplifier with name of the class A, B, F, etc. So first of all, we must find a very good semiconductor, if possible, high efficiency and high power. And even if we find a good semiconductor, next we must design the good amplifier circuit. So we have two stages: find a good semiconductor and design a good amplifier. And this is a very simple, real developed microwave amplifier by my student. Here you can see we put FET in this case. And here you can see the matching circuit and additionally bias circuit here. And it's enough to develop the microwave amplifier for the wireless communication system. But in this figure, this is a very low power and low efficiency amplifier. And if we would like to increase the efficiency, we need more technology of the circuit. And this is the basic information of the theoretical parameter of the, for example, stability of the amplifier. You've already run S parameter, scattering parameter S. And when we measure the S parameter of the transistor, FET, HBT, etc., and with help of this S parameter, we can calculate the integrated impedance here. And with help of this parameter, we can estimate the stability of the amplifier. So here you can see there are a lot of S parameter here. And best solution is both parameters will be below 1. And if this parameter is over 1, this amplifier will not be stable, and this amplifier becomes generators. So when we design the amplifier, and we have to measure this parameter, and we have to check this optimum condition of the stability of amplifier. And we have the other parameter to estimate the stability of the amplifier, K factor and D factor. K describes the condition to be maximum average gain, and D describes D indicates a guarantee of the stability. Both parameters are very important. So stability without any condition, condition of no oscillation against all passive signal source impedance and load impedance. So this stability, no generation, is very, very important to design the amplifier. And this is the other parameter, maximum average gain, MAG. And when we measure S parameter, we can estimate the gain of the amplifier ratio between the input power and the output power. So usually, typical power amplifier have a 10 dB gain or 15 dB gain. So of course, higher gain is better, but we must consider the limitation of the maximum available gain from the S parameter and the K parameters. This is the basic data, and from here I would like to explain the semiconductor device itself. And this is a typical semiconductor device, mainly 3-port device for the microwave frequency. Most FET sometimes apply in the microwave circuit. And CHEMT and FET, HBT are the very high power device and high efficiency devices. And in the microwave amplifier circuit, we sometimes use a HEMT or HBT or MES FET. MOS is a very cheap device, and we apply mainly MOS FET for the lower frequency application. This is a classification of the semiconductor 3-port devices. For the lower power, gallium arsenide HEMT apply. And when we increase the frequency, we have a limitation of the frequency of the silicon itself. And for higher frequency, we need a gallium nitride or gallium arsenide. So, but I remember about 30 years ago, silicon could not be applied in the microwave frequency. About 30-40 years ago, silicon could be applied only megahertz devices. But recently, we can apply the silicon devices not only microwave frequency, but also millimeter wave application. And my Japanese friend, professor, is developing terahertz silicon technology. So year by year, technology is advanced. So about 30 years ago, I did not believe silicon could be applied in the microwave frequency. But recently, we can apply the silicon on the journal paper to the terahertz frequency. So I will explain later. Recently, we are expecting the wideband gap new semiconductor silicon carbide or the gallium nitride. And just now, silicon carbide as a wideband gap devices is applied for the megahertz device or the power source circuit only. For example, for the power source for the electrical vehicle or the other. But gallium nitride is expected to the microwave frequency. But we've already run history of the silicon. So in near future, if user requests, silicon carbide can be used in the microwave frequency, hopefully. But just now, we can use the gallium nitride only in the microwave frequency. And these parameters are very important parameter to describe the limitation of the frequency with semiconductors FT and Fmax. FT indicates the unity current gain frequency, and the Fmax indicates the frequency at the maximum power gain is equal to 1. It means this is a limitation of the amplifier frequency. So if we find the semiconductor with Fmax is, for example, 1 GHz on the catalog, and this semiconductor unfortunately cannot be applied in the 2 GHz amplifier because amplifier gain limitation, frequency limitation of the gain is 1 GHz in this case. So we must check this FT and the Fmax to design the microwave circuit. And additionally, I will explain in the end of this talk, to increase the efficiency, we have to use the higher harmonics to add the more to add the more power and more efficiency. So if we find, for example, F max is 3 GHz, it seems we can use this semiconductor with F max of the 3 GHz at the 2 GHz amplifier. But if we would like to increase the efficiency, we have to use harmonics, and in this case, we need higher F max, for example, 10 GHz or 15 GHz, to treat the higher harmonics. So please remember this parameter, F max and FT. And this is one example of the arsenide FET short channel model. And so, as you know, we have the source gate drain on the very low frequency transmitter. It's an emitter, ground, source, etc. But in the case of the gallium arsenide, it is named the source gate drain. And these are typical parameters of the gallium arsenide FET. And FT is here. And FT is decided by this equation. And if we would like to increase the frequency, well, we would like to increase the FT or F max, we have a two-way. We must develop the shorter LG. LG is where length of the gate here. It means speed of the electron is limited. So if speed of the electron is limited, what we need to increase the frequency is to become a short distance to move the electron. So it's very easy to understand. So silicon, now we can apply higher frequency to develop very short gate transistor. So this is a simple reason to increase the frequency on silicon. And will be increase the frequency on the silicon carbide, etc. And additionally, if we can develop the high voice saturation, we can increase the frequency, corresponding frequency. And to increase the voice saturation, we need a new material, as I mentioned. So instead of the gallium arsenide, for example, we need a gallium nitride, etc. And this is the equivalent circuit of the gallium nitride, gallium arsenide, FET. And it's a case of the low power. And so, as I mentioned in the first day, we can change the semiconductor itself as an equivalent circuit with LC, R, etc. So, but if we increase power on the semiconductor, parasitic part will be occurred. So, if we add much power, higher power onto the gallium semiconductor, we must add these parasitic elements. So, usually on the catalog of the semiconductor, these parameters are shown in the catalog, but it's mainly a low power situation only. So one famous Japanese professor, he can develop a very good amplifier, told me we have to know these parasitic parameters on the equivalent circuit, but if we would like to measure these parasitic elements, we have to pay huge budget to measurement company, he said. So, but if we have these parasitic elements inside the equivalent circuit of the semiconductor, we can design the very good amplifier or the microwave circuit. And when we change the material, we can increase the frequency or we can increase the power efficiency. So, as I mentioned, now we are expecting a new material of the silicon carbide or gallium nitride, and in the near future, we are expecting a diamond and gallium oxide. So this is a typical figure to explain the relationship between the electric field and the velocity. Velocity means the velocity of the electrons. So compared to the silicon or gallium arsenide, this velocity, electron velocity is very high and it's high speed. Means we can apply the higher frequency devices. And recently, in the microwave wireless power transfer research, there are a lot of good amplifier design with gallium nitride mainly. And one of my students checked the old paper, journal paper of the amplifier with gallium nitride, and he made this figure. So this is a relationship between the frequency and output power of the gallium nitride amplifier. And here you can see we mainly use 2 GHz or 5 GHz as a WPT business now. And now, but this data is a little bit old, so about 5 or 10 years ago, we have already reached the over 500 watt amplifier at around the 2 GHz. And when we increase the frequency, of course, it's a natural phenomena, power decreases. But around the 10 GHz, now we have approximately 100 watt output power amplifier here. And these are papers. If you are interested in, please check the IEEE Explorer. And this is the viewpoint classification of the gallium nitride amplifier. Power and efficiency. And in this case, my student checked S1, mainly 2 GHz amplifier design. And if power is very small, efficiency has already reached about 80%. And if power increases, of course, efficiency decreases. It's a natural phenomenon. And these are checked papers. And when we increase the frequency to the 5 GHz C-band, it's the same, but here you can see power and efficiency are a little bit decreased compared to the S-band, 2 GHz. But now about 10 years ago, we've already reached about 70% conversion efficiency of the gallium nitride amplifier. And so we have a few hundred watt amplifiers at C-band, 5 GHz. And this is the paper. And if possible, we would like to increase the frequency, as I mentioned yesterday, to focus the wireless power into the 1 point. So X-band around the 10 GHz, there are a lot of interesting works and journals in IEEE, because in X-band, they use this microwave as a military application. So my student checks the journal paper, and when we consider the 10 GHz amplifier, efficiency decreases to the around 60%, and the power now 100 watt or 200 watt. It's a natural phenomenon. When we increase the frequency, power decreases and efficiency decreases. But we've already reached about 60% of the power conversion at around the 10 GHz amplifier. And these are the original source. So from here, next I'd like to introduce circuit design itself. Now you've already run device itself. And next, we use this device, and we have to design the circuit. So now, first of all, this is a basic circuit of the amplifier named class ABC. This is a classification of the circuit design of the amplifier. ABC, we use the same circuit, but we change the bias voltage in each circuit. And but unfortunately, in class ABC amplifier, we cannot reach theoretically 100% conversion efficiency. So in class D, E, F, and recently JR, we add the output filter to reuse the harmonics to increase the efficiency up to 100% theoretically. So recently for the wireless power transfer, class A for JR applied. So in order, I will explain basically ABC and the next DEF, JR in my talk. And in the IEEE journal, there are a lot of different amplifier names, Doherty amplifier, LNC, EER. But these amplifier, combination of the amplifier to expand the corresponding power or to expand the wave bandwidth for the wireless communication. So for the wireless power transfer, we don't use this Doherty, EER, and today I skip this. So first of all, I would like to introduce a very, very basic amplifier design of the class ABC. It's the same. Here you can see the semiconductor device, FET, HBT, etc. And we connect this emitter here. And here is the source, and here is the output. But this is a very basic, and to check the stability factor K or etc. It's not a stable circuit, and there is no power line to add the bias voltage to this semiconductor. So in the real, we usually use this circuit. We add some bias line or the feedback loop to stabilize this circuit, etc. So with this circuit, we can develop the basic amplifier of the class ABC. And as I mentioned, in the class ABC, circuit is the same. So a difference is just a bias voltage to add the voltage to this semiconductor. So this is a very basic explanation to describe the relationship between the bias voltage and current in the semiconductor. And class A is a very, very basic amplifier. And bias point is here. So midpoint of the voltage, bias voltage and the current. And when we put this bias voltage here, and input signal is smoothly amplified to the same shape of the output signal. And so in this bias point, the waveform of the voltage and current is here. And voltage is very simple continuous wave, and current is the same, very pure continuous wave only. So there is no harmonics, and it's very beautiful waveform. But theoretically, in this case, theoretically efficiency is 50% only. And this efficiency is calculated from the this overlap of the V and I as a loss. And so here you can see there are a lot of overlapping points on the V and I. So in this class A, theoretical efficiency is only 50%. And class B, we move the bias point to the limitation of the current is 0. And in this case, we add a very good bias voltage, and here is a waveform of V and I. And in this case, voltage waveform is a very pure sinusoidal, but current waveform is a half-wave waveform in this case. So, fortunately, from this waveform of the current, harmonics occurs and efficiency decreases, but overlapping point, total overlapping area decreases. So, if we develop this push-pull amplifier, and the positive and negative circuit is combined into one, and we add this half wavelength as a negative waveform, we can reach the theoretically 78.5% in the class B. And here you can see we can move, we can add more bias voltage here. But in this case, current is reached a very strange point. So theoretically, class C, we can reach 100% maybe, but output signal waveform is very, very strange, and usually we don't use class C as an amplifier. So this is the summary of the VI characteristic of the class ABC amplifier. Here is the class A, and efficiency theoretically 50%, and here class B, but the theoretical homogeneous efficiency is 78.85%, and the class C is here. So this is a very basic amplifier. But as I mentioned now, if we choose a class C, of course, we can reach 100%, but our waveform is very strange. So in this case, our limitation of the theoretical homogeneous efficiency is about 80%. So we need more 20%. So first of all, I'd like to introduce class D and E in order. So as I mentioned, based on the class ABC amplifier, we add the extra output filter. And in this case here, we add this series resonator, L09 resonator on this class B push-pull amplifier. And caused by this series resonator, we can change the waveform as a V and I, and as a result, theoretically, we can reach 100% by this class B amplifier. But this is a working principle of the class D, but theoretically, we can reach 100% efficiency, but it's unfortunate in the real device, we have a saturation voltage, and switching time is also finite. So in the real, efficiency is never 100%, and this saturation voltage was a frequency program. Usually, this class D is not applied as a microwave frequency. Usually, this class D, you find the paper of the class D in the lower frequency application, sometimes inductive WPT or etc. And we increase this alphabet D to E. And here you can see there is no push-pull, but we add the other series resonator here. And this combination of the resonator and the capacitance, we can realize this from chains, and we can increase conversion efficiency. And this is the frequency limit of the class E amplifier in this paper. And for example, they developed the gallium nitride film class E amplifier, and they reached 2 gigahertz alone. So sometimes we can apply this class E amplifier, and this is the computer simulation result. And this waveform is a little bit strange compared to the class ABC, but this waveform creates the very few loss amplifier, and efficiency is close to 100%. But class E, so I'm not sure there are a lot of class E amplifiers for the radiative WPT in microwave frequency. Usually, we find a lot of excellent journal paper to describe the class F amplifier. So compared to these two class A and class E and class D, in the class F, we have the same resonators here to create this relationship of the impedance 0 at the even harmonics and infinity at the odd harmonics. And sometimes we can change this relationship at the even harmonics. Impedance becomes infinity, and odd harmonics impedance is 0. And this first case, we named it class F, and second case we named it class inverse F. And with help of this quarter length distributed line, this resonator can be create this impedance relationship. And as a result, theoretically, drain current and drain voltage of the class A amplifier can be described this formula. And this formula is written in this figure. And here you can see a very beautiful half-wave current and a very strange rectangular shaped voltage. And this is caused by this relationship. And this V and I is created from this relationship of the impedance. And here you can see there is no overlapping of the V and I. So as a result, theoretically, it's the same as a class E and a class D. This class A amplifier can be reached 100% conversion efficiency. And additionally, we can explain this operation of the class A from the class A or class B. And now I mentioned we consider to change the harmonics at the auto frequency and even frequency, and impedance is 0 and infinity. And if we don't use any harmonics, and we don't use any relationship of the strange impedance, in this case, we use only a very pure main signal only. In this case, this is named class A. And class B, we change the bias voltage. In this case, ideally, class B can be realized with help of the current, even frequency of the current harmonics. And in the class B, we don't use auto harmonics of the voltage. So when we studied the class A amplifier with the main frequency only, and when we change the bias voltage, we can reach a class F here. And in this case, we use even harmonics of the current. And additionally, we add the quarter length distributed line and the resonator, and this class B operation move to the here with help of the auto harmonics of the voltage. So at last, we reach theoretically 100%. Of course, this is the ideal case. So we cannot use the all infinite auto mode, infinite auto harmonics, and infinite even mode. So usually, so second harmonics or fourth harmonic or 3 or 5th harmonic are limit in the real circuit. So in this case, we can reach 90%, 85%, etc. So it's easy to understand. We compare the waveform in each case. Class A, as I mentioned, so we use a main frequency only, so very pure sinusoidal wave on the current and the voltage. And in class B, so this current becomes a half wave, and current, in this case, current use even harmonics mainly. But voltage is a very pure sinusoidal and main frequency only. And at last, we apply the class A, and this current is the same as the class B. But this voltage changes with help of the harmonics. So this is the operation of the class F amplifier. And we can see the relationship between relationship of the impedance in each frequency. Here you can see this is a Smith chart you've already run. And this second harmonics is here, and third harmonics is here. It's an infinite point. And of course, fourth harmonics and fifth harmonics, and so we must design this resonator on this Smith chart here. So this is one computer simulation result of the class A amplifier on the Smith chart. And this is an example of the developed class F amplifier with gallium nitride. This is Japanese amplifier. And it was a very low amplifier at about 2 GHz, but at the time, efficiency, power efficiency of the amplifier reached 72%. This is a very excellent number compared to the class B and the class A. And Japanese group increased the frequency to 5.8 GHz, and in this time, they've already reached 80% in this amplifier. And it's very clear figure. Here you can see a resonator in each harmonic. And we change the length of this line open stop, and we can create the relationship of the impedance 0 infinity, 0 infinity by this peacock wings. So this is a typical design of the class F amplifier. And recently, for the WPT experiment for the solar power satellite, Mitsubishi Electric Company developed this MMIC class F amplifier at the C-band, 5.10 GHz. It's not clear, but around here, they add impedance matching resonators there inside the MMIC. And in this time, they reached about 70% as a power added efficiency. So, if possible, you should use this class F amplifier mainly for wireless power transfer, because in my at the first of my today's talk, I showed you the recommendation and requirement for the wireless power transfer. We don't need any modulation for the microwave because we use a carrier only. So I explain again and again, we add a resonator circuit here. Resonator means bandwidth for the optimum efficiency, bandwidth for the optimum efficiency area is very narrow, because if we must realize this relationship of the 0 and infinity impedance, we must add a very high Q resonator, and if we develop the high Q resonator, bandwidth is very, very narrow. So this class F amplifier usually use wireless power only, because we don't need any modulation. We don't need a very wideband radio waves. So if we would like to apply this class F or class D or class E, we have to consider how to keep the high efficiency, but how to increase the bandwidth. It's very difficult problem. So, but this class F amplifier is suitable for the wireless power transfer, because there we don't need any bandwidth to carry the electricity on the radio waves. So, and additionally, recently Japanese famous professor of the amplifier proposed the class J and class R, because, as I mentioned now, when we would like to develop the class F amplifier, this relationship of the impedance must be 0 and infinity. This is very, we need a very strict design of the resonator. And when this impedance move to the other point, efficiency decreases. So we need a very strict design of the class F amplifier. Very famous Japanese professor considered. So instead of this class F amplifier, he proposed class J and class R. This is a comparison between the JFR and additionally BE. And there is an important point. Class F, for the two second harmonic, impedance should be 0, and the third harmonic infinity. But in class J, infinity is the key, but for the second harmonic, we don't need the impedance of 0. And instead of the 0 impedance, the same efficiency, very good efficiency, can realize the constant resistance, he said. Of course, compared to the 0 impedance, in the class J, he used the constant resistance, and the efficiency, maximum efficiency, does not reach the 100%. But based on this class J concept, at last, class R, he changed this third harmonics impedance to the JX and second harmonics JX. So this is a relationship between the class J and class R amplifier. So through this outside of the Smith chart, we put these impedance points. And as a result of the relationship of this impedance point, mean plus minus Jx and plus minus Jx, theoretically, this class R amplifier is 100% conversion efficiency, he said. And compared to this class JFR, class B and class E is this impedance relationship. And so, as I mentioned, class B cannot reach our theoretical 100% and theoretically 78% only. And class E, as I mentioned, with help of the resonance circuit, we can reach 100% here. So this is a very important figure to show the difference between these class amplifiers. So this is a waveform and class F and class R. This is a class F and this is a class R amplifier. So this is a very beautiful class F waveform. Of course, compared to this class F waveform of the class R is a little bit strange, but design, selection of the design is very loose compared to the class F. So he proposed recently class R is better to develop real circuit. So this is a very brand new amplifier of the class R and class J. So this is a load condition on the Smith chart of the class F and class R here. So I suppose that's just good time to close my today's talk. So today I showed you how to design the amplifier as a transmitter of the wireless power. So please go back to the first figure, first presentation. For the wireless power transfer, we need high power, high efficiency, and not expensive, cheap devices. And but instead of this high requirement, we don't need any modulation. It means we don't need any bandwidth to design the amplifier. And low noise is a very important point, but this requirement is a little bit far from the wireless communication. So based on this requirement, I recommend you to use a class R or class F or class R to increase the efficiency up to 100%, for example. So this is today's my morning talk. So thank you so much.
Any query? Any question? Oh. Anyway, thank you.
Yeah, and in this afternoon, I refocus this cost. So semiconductor device and the circuit is very expensive compared to the microwave tube. So in this afternoon, I recommend you to use a microwave tube to realize the cheap WPT system. It's an afternoon talk.